Hello all, I'm J.R.Sofia, Assistant Professor of Physics at Fatima College, and in this video we are going to talk about Shockley Quasar limit. So what is Shockley Quasar limit? It is the upper limit to maximum achievable efficiency of a solar cell based on fundamental physics, material properties and the nature of incident solar radiation. As we could see in this figure, it is the efficiency plotted versus band gap of the absorber. For material with a band gap around 1.34 electron volt, the efficiency reaches a maximum value of around 33.7%. So this is the Shockley-Quasar limit. We say that we cannot reach beyond 33.7% efficiency for a solar cell. Why is this happening? What are the limiting factors involved? That is, we are going to discuss. Assumptions or conditions. Each incoming photon, it is going to create only one electron hole pair. Further generation of electron hole pairs are not considered under this study. Photovoltaic material or the absorber has a single band gap. Photons which are having energy lesser than that of the band gap, it is not being absorbed. Photons with energy higher than that of the band gap, they are absorbed. The excess energy, it is used to it is transferred to the electron hole pair, and they collide with the molecules involved, and which is lost by thermalization or thermal relaxation. The mobility of the charge carrier is ideal and is infinite. That is, even though there are so many hindrances involved, the charge carriers are able to travel to the positive and negative electrodes regardless of the hindrances involved. Loss of electron hole pair is only through radiative recombination. Elimination of solar cell, it is unconcentrated, and they are under standard conditions of 1000 watt per meter square at 300 kelvin, 27 degrees Celsius, with a air mass of 1.5. We know that elimination of solar cell is not at all constant, but still we assume that way. Sun is going to be considered as a black body at temperature of 6000 Kelvin, and solar cell is a black body with the temperature of 300 Kelvin. Limiting phenomena involved in limiting the SQ limit to 33.7% efficiency. First point is that there is a mismatch in the spectrum of the solar radiation spectrum. As you could see in the right side, the solar irradiance, it is plotted versus wavelength, and at around 500 to 700 nanometer, the spectral irradiance is achieving a peak, whereas there is lesser number of photons in the IR radiation. The graph is conveying that there is more number of photons that is being received from the solar radiation lies only in the visible region, whereas there is photons generated by the solar radiation but in the infrared region, but the number of photon is far less when compared to that of the visible photon. So if I have a material which can absorb wavelengths in the IR radiation, the material is capable of, even though it is capable of absorbing, photons are very less in that region, and so it is not going to contribute to the efficiency rise. Hence there is the spectral mismatch is the first reason. And if I have a material which is having a band gap of certain value, wavelengths which are having energy lesser than that of the band gap, they are going unabsorbed, whereas photons which are having higher energy than the band gap, they are being absorbed, but they are going to create loss of energy by thermalization or thermal relaxation. These all contributes to the cumulative effect of limiting the efficiency to 33.7%, only if I have a band gap of 1.2 electron volt to 1.34 electron volt. This deviation from the band gap is going to always reduce the efficiency. This is contributing to 48% loss. The second kind of loss is radiative recombination. If a photon can generate an electron hole pair, obviously when an electron combines with the hole, it is going to result in generation of a photon. In such a way, where photon is being released due to recombination, we call such recombination as radiative recombination. This is always present in a solar cell. Black body radiation. Black body is an entity which is going to emit characteristic radiation depending upon the temperature of the material. In this case, solar cell is also considered to be a black body. It is going to absorb, so what how if it is in thermal equilibrium with the surroundings, it is going to emit the same amount of radiation that is owing to its temperature. This is contributing to 7% loss of incoming radiation, which is being let out by the solar cell as a radiation. called this is black body radiation loss. The next kind of loss is for voltage losses. As we know, band gap of the absorber, it is going to determine the open circuit voltage of a solar cell. It can be only about 40% lower than the band gap. But we know that only if I have a material which is around 1.34 electron volt band gap, uh, then we can reach the maximum efficiency of 33.7%. With that in hand, we can only generate a solar cell with a VOC around 1 electron volt. As we can see, if I have a band gap of 1.7 electron volt material, and it is going to result in a VOC of 1 volt, which is limiting the performance of the solar cell. Fill factor loss. We know that efficiency maximum power point is a point where the maximum power that can be tapped from the solar cell. Depending upon this solar illumination and temperature and incoming temperature of your device, the solar irradiation is going to vary, as well as the maximum power point will also vary. This is going to limit the fill factor, and this non-ideality behavior, it is going to contribute to fill factor loss. When these all losses are being added together to calculate the SQ limit, which is the 33.7% upper limit for the solar cell.